When your model says 90% sure, is it actually right about 9 times out of 10? We'll check that with one simple plot. You have model probabilities, but you do not trust them. That breaks things like risk decisions, pricing, and automated alerts. By the end, you will know how to check if probabilities are honest, compare two models, and fix miscalibration with a simple calibration step in Python. I'm Professor Pi, teaching AI foundations with simple Python. Calibration curves solve a clear problem. Models often give a number that looks like a probability, but that number can be overconfident or timid. A calibration curve plots predicted probability against the actual frequency of the positive class. If points follow the diagonal line, probabilities are honest. If they stray, you need to adjust them before you make probability-driven decisions. Imagine a classifier that says many examples are 0.9 likely to be positive. If only half of those turn out positive, the model is overconfident. Calibration fixes the mapping from model score to real-world frequency. It is cheap, interpretable, and crucial when you care about expected values or decisions, not only ranking. We will build a small toy pipeline. First, we train a logistic baseline and collect its probabilities. Next, we compute a calibration curve and a simple expected calibration error. Then we train a decision tree, compare calibration quality, and if needed, calibrate the tree with isotonic regression. Finally, we measure improvement with the Brier score, so we know calibration helped in practice. Now we train a quick baseline and collect probabilities. This snippet trains a quick baseline classifier and collects its predicted probabilities. We use scikit-learn's make classification to generate a simple binary dataset, then slice it into a training and test split. LogisticRegression is fit on the training set, and predict-proba returns the positive class probability vector P on the test set. Keeping the train and test split explicit makes downstream evaluation honest. The printed mean pred shows the average confidence of the model on the test set, which you can compare to the actual positive rate later to judge calibration. Next, we compute the calibration curve and a simple miscalibration score. This snippet computes a scikit-learn calibration curve to test probability honesty. The function calibration curve returns PT, fraction of positives, and PP, mean predicted probabilities across bins, letting us see how predictions align with reality. We summarize this visually oriented curve with a simple expected calibration error, ECE, by averaging absolute differences between PP and PT. A smaller ECE means predicted probabilities better match observed frequencies. Increasing n-bins makes the check more granular but noisier with limited data. Fewer bins smooths noise but may hide miscalibration. A low ECE in the printout signals trustworthy probabilities. Now we train a second model and compare which gives better probabilities. This snippet compares calibration quality between two models and selects the better one. We train a scikit-learn DecisionTreeClassifier on the same data and compute its probability vector P2 on the test set. Using calibration curve again, we derive ECE2 for the tree by averaging the absolute gaps between predicted and observed frequencies. Finally, we pick the model with the smaller expected calibration error, reporting better model as LR or tree. Trees can be overconfident by default, whereas logistic regression tends to be more calibrated. The printed choice highlights which one you should trust for probabilities. If the tree is worse, we will calibrate it using isotonic regression wrapped with cross-validation. This snippet calibrates the tree's probabilities using scikit-learn's CalibratedClassifierCV. We wrap the trained decision tree classifier with method equal isotonic, which learns a non-parametric mapping so predicted scores better reflect observed frequencies. The calibrator is fitted on the training data with cross-validation, CV equals 3, to avoid leaking test information. We then run calibration curve on the calibrated probabilities, PC, and recompute the error, ECEC. Isotonic is flexible and can reduce miscalibration more than sigmoid, but it may overfit with tiny datasets. Sigmoid is smoother and faster. A lower ECE after indicates calibration made the tree's probabilities more trustworthy. Finally, we score the practical improvement with a proper probability loss. This snippet quantifies practical improvement using scikit-learn's Brier score. The function Brier score loss measures the mean squared error of probabilities against outcomes, so lower is better calibrated and sharper predictions. We compute B0 for the original probabilities P and B1 for the calibrated probabilities PC, then report the gain as the difference B0 minus B1. Positive gain means calibration reduced probability error in a way that directly matters for decision costs. A positive Brier gain in the output confirms the calibrated model is a stronger baseline for probability-driven decisions. In a real project, you would swap toy data for your dataset and keep the same checks. If your class balance or feature drift changes over time, rerun the calibration check regularly and refit the calibrator on fresh data. Calibration is cheap compared to retraining the whole model, and it plugs into most binary pipelines easily. Recap. Calibration curves show whether predicted probabilities match observed frequencies. Use them when probability accuracy matters for decisions, thresholds, or expected values. One caveat: small test sets or too many bins can make the curve noisy and mislead you. Next step, run the same pipeline with a larger holdout or cross-validation folds, and compare isotonic versus sigmoid calibrators to see which generalizes better. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.